So disaccharides are two monosaccharides joined together. And this happens because one of the monosaccharides acts as a hemiacetal and the other acts as an alcohol. Remember, we made acetals by reacting a hemiacetal with an alcohol. So here we've got one monosaccharide acting as the hemiacetal, that's this anomeric carbon here, which has the ether linkage and the alcohol group on it. And another monosaccharide can function as an alcohol, and they will give off a water molecule here. It's a condensation reaction, and this oxygen will become bonded to this carbon over here. And so now we have two monosaccharides joined, and this is called a glycosidic linkage. It's the bond in a disaccharide that links the two monosaccharides together. These monosaccharides can be the same monosaccharide or they can be different monosaccharides, and so you can imagine there's lots of different possibilities for combinations. We're only going to talk about a couple of them. Maltose is also called malt sugar. This is produced when starch breaks down, and it's found in malt. That's why it's called malt sugar. Malt sugar is composed of two D-glucose units, and the glycosidic linkage is called an alpha 1 to 4 linkage. So here we have the linkage. So on this carbon, on this sugar, which was acting as the acetal, this is in the down position, which is the alpha position. So that's where alpha in the linkage name comes from. That's alpha. And it's a linkage between the 1 carbon and the 4 carbon. So that's the alpha 1,4 linkage. Maltose is a reducing sugar, and it does open up the glucose on the right still has its anomeric carbon open. It's still a hemiacetal, and so this can open up and it will change its configuration. This is beta maltose, and if it opens up again and closes, it can also form alpha maltose. And so you have a mixture of those two forms. Because we have this point up here maybe. The hemiacetal unit here, this is a reducing sugar. If you hydrolyze maltose, so adding water to it, and you need a catalyst like acid or the enzyme maltase. Maltase acts on maltose. The ASE tells us it's an enzyme. Then you'll get 2 D-glucose units because that's what maltose is composed of. So you should know that maltose is 2 glucose units with an alpha 1,4 linkage. So let's look a little more in depth at these notation for glycosidic linkages. So the numbers tell us which carbon atoms are linked, and the alpha and betas give us the configuration. So on this monosaccharide, this oxygen is in the alpha position, and it's connecting to carbon 4 on the other monosaccharide, and so that's alpha 1,4. This is an example of the beta 1,4. So here, this is in the up position, the beta position, still connecting from 1 to 4. And which type of linkage there is pretty important. And we'll see these glycosidic linkages in several different types of compounds. Cellobiose is another disaccharide. This is an intermediate in the hydrolysis of cellulose, which is a polysaccharide that we'll talk about later. It contains 2 beta D-glucose units. So here's 1 beta D-glucose. This one doesn't really matter because this one can open up and close up. But here with a beta position here, this is reacting with that, and we form this beta 1,4 linkage. And so this is up at an angle instead of down. this linkage is also always going to be in the same position. It's this one that can be either alpha or beta. So when you take cellobiose and you hydrolyze it, here the enzyme would be cellobiase, you also get 2 D-glucose units. So maltose and cellobiose are both disaccharides of glucose. The difference is in how they are linked together. Cellobiose is a beta 1,4 linkage and maltose is an alpha 1,4 linkage. They have very different biochemical behaviors because of that linkage. Humans have the enzyme maltase, and so we can digest maltose. And yeast also has that enzyme, and so yeast can digest it and ferment it, and that's why you've heard of malt liquor or malt liquor. It's made by fermenting maltose, a substance, it's from barley, I believe. And so it can digest that. Cellobiose cannot be digested by humans or fermented by yeast because we don't have the enzyme necessary to hydrolyze the cellobiose. So even though they're extremely similar, that one difference in how that linkage is oriented makes it either digestible, we can use maltose and get nutrition out of it. Cellobiose, we can't. That just ends up being fiber. Another important disaccharide is lactose, or milk sugar. This is another reducing sugar. It's composed of beta-D-galactose and D-glucose, and these are joined by a beta-1,4 glycosidic linkage. So this linkage is more like the cellobiose. So here's galactose and glucose, and this bond with the oxygen is in the up position, so it's a beta-1,4. If you hydrolyze lactose, you get glucose and galactose. And the enzyme necessary there is lactase. Now, there's an interesting section in your book about lactose intolerance. Most humans are able to produce lactase and metabolize lactose sugar just fine as infants, but then as they get older, they lose their lactase enzymes and become lactose intolerant. And it turns out it's actually a minority of people that retain the ability to digest lactose through adulthood. So if you don't get along with milk, you're in good company.
Why is it that some people have lactose intolerance early on and then they end up being tolerant of it later?
I'm not sure that can really happen. You can have temporary lactose intolerance when you have antibiotics or you get intestinal problems. Everything gets kind of out of whack.
Like my boyfriend, when he was a kid, he couldn't have milk at all, any milk products, but now he can.
Was it lactose intolerance or a milk allergy?
Any kind of
Because there's milk allergy. Yeah, a lot of people get them mixed up. A milk allergy is where your body actually produces antigens to substances in the milk. And a lactose intolerance is not an allergy. It's just that you can't digest the lactose. And you can use Lactaid milk, which has lactase enzyme added to it, or Lactaid tablets or something to help you digest it. And then you'll be fine. If you have a milk allergy, doing something like that won't help at all. Sometimes it's a lot more common for people to have milk allergies when they're young. And if they avoid milk, they sometimes outgrow them and then can handle milk when they're older. I am not an expert on that, but that's my 2 cents. Sucrose. Sucrose is by far the most abundant disaccharide, and this is table sugar. It is found in fruits and obviously in sugar beets and sugar cane. And it's composed of alpha D-glucose and beta D-fructose connected with an alpha beta 1,2 glycosidic linkage. So this is a little different than the ones we've looked at before. So what happens here is we've got the anomeric carbon on the fructose and the anomeric carbon on the glucose connecting. So it's more of a head-to-head connection instead of a head-to-tail, because most of them have been with the 4 carbon on the second glucose unit or second monosaccharide. These are connecting at both anomeric carbons. And so on the glucose, it is an alpha linkage, and on the sucrose, it's a beta linkage. And so they end up being having a very different shape. The sucrose then is a non-reducing sugar. There's no hemiacetal to react. It has 2 acetal centers, and there's no open chain form. So let's go back and look at that. The reducing sugars act here at this anomeric carbon, the hemiacetal. There is no hemiacetal here. This is an acetal. This carbon has 2 ether linkages. It's not going to act as a reducing sugar. This one also has 2 ether linkages. It's an acetal, so it's not going to act as a reducing sugar either. And these chains now cannot open. They're stuck in the closed position. These other disaccharides, this is an acetal here, and so that can't be a reducing sugar. But this one over here is still a hemiacetal, and so that can be a reducing sugar. So sucrose is not a reducing sugar. When you hydrolyze sucrose, you end up with D-glucose and D-fructose, the 2 components, and this is sometimes called invert sugar. The reason it's called invert sugar is because when you hydrolyze the sucrose, the direction of the rotation of the light changes. So I think it goes to the right for sucrose, and then it actually rotates to the left for the invert sugar. And so that's why it inverted the rotation of light, so that's why it's called an invert sugar. And this mixture of glucose and fructose is very similar to what's found in honey. So honey is a lot like hydrolyzed sucrose. And there's a lot more information in your book about that. Another common glycosidic linkage is alpha-1,6. So here on this monosaccharide, we have an alpha from the 1 carbon, and now this is connecting with the 6 carbon, which is that CH2OH group that kind of sticks up like a flag, this guy. So that's an alpha-1,6. So remember, the carbons are numbered 1, 2, 3, 4, 5, 6. And so the 1 to 6 just tells us where it's connected. Any questions? Well, let's look at these questions. Which of these disaccharides, maltose, cellobiose, lactose, and sucrose, has each of the following structural or reaction characteristics? There may be more than one answer for a given characteristic. 2 different monosaccharide units are present. What were the 2 monosaccharides in maltose? There's 2 glucose units, right? And cellobiose was 2 glucose units just hooked together differently. But lactose was galactose and glucose, so that's a positive for A. And what are the 2 monosaccharides in sucrose? Fructose and glucose. So pick a color. Blue. It's a blue day, officially now. So lactose is one of those, and sucrose. This morning they picked black. I'm feeling gloomy, I guess. Which of these does hydrolysis produce only monosaccharides? It's kind of a trick question. All of them? Yeah.
I thought we were choosing those 2.
Yeah, no, we're choosing out of these 4, and all of them, when you hydrolyze them, because they're disaccharides, if you hydrolyze them, you get 2 monosaccharides. So all of them, all 4. Okay, which one has its glycosidic linkage as a head-to-head linkage instead of a head-to-toe? That's the one that looked
Sucrose?
sucrose. It looks more like that, where they're both going off to the same side, because this is to the 2-carbon. I think I got something wrong there, but the idea is right. And now I'll erase it and get rid of the evidence. So sucrose has a head-to-head linkage instead of a head-to-toe.
What is, I don't get the head-to-head versus the head.
Okay, that's a good question. Let's go back and look at it. Okay, so let's look at the head to tail. So here's lactose. And here, this is carbon 1. That's like, you could think of the head of it. And this is carbon 4, which is at the end. So this would be considered the tail. So this is head to toe or head to tail. And then on the sucrose, here we have the head of one connected to the head of the
So
other.
it always have to be 1 to...
For this one, it's 1 to 2. It's 2 because this is a ketose and not an aldose. And so there's this CH2 group down here. It has 6 carbons, but it only makes a 5-membered ring because we have 2 of these guys hanging off, one at the end and then one at the beginning. So if it's like a 1 to 1 or a 1 to 2 linkage, it's going to be head to head. If it's 1 to 4, 1 to 6, it's a head to toe or head to tail. I'm not sure which. And the important difference here is both of the anomeric carbons, both of the hemiacetal centers on these are occupied now. They have both become acetals. And so that takes away the reducing sugar business because we don't get a reaction there anymore. Good question. What? Okay, so which one of these is not a reducing sugar? The sucrose. Because of that head-to-head. There's no hemiacetal center to react. Just a little lost today. Okay, so drawing structural formulas. Draw structural formulas for the products formed when the disaccharide lactose is hydrolyzed. So when this guy is hydrolyzed, meaning we're going to take water and add it in here and break this into 2 monosaccharides, what are we going to end up with? Well, let's kind of have the water fly in there and see what happens. So H and OH. What we're going to end up with is an OH on this monosaccharide and an OH on this one. So we could envision this is going to the oxygen and this one going in here. And so the one on the left would look like this. Most of this I'm just copying down what was already there. And then that was in the beta form, so I'm going to draw it in the beta form. But remember that monosaccharides like this open and close and open and close, and so they naturally form the alpha and the beta forms. And the one on the right now, it's showing that straight out, and your book usually uses a squiggly line there, because that means it could be either, which is what we should have done with the first one, but we can fix it. Now, what position is this OH going to be in? Is it going to be down or up? What is it doing here to start with? It's down. So that orientation cannot change unless one of these bonds is broken, and that's not going to happen. The orientation of this carbon changes because this thing opens and closes all by itself. So this one will be down. And probably a more accurate way to draw this one would be little squiggly lines sticking straight out. And that just indicates that the orientation there is not specified. Any questions?
So any questions would be not specified?
Well, when this hydrolyzes, whatever orientation or configuration is there is not going to stay because the ring opens and closes, and when it closes again, it could close in either orientation. Any other questions?